All right. For our last topic, we're going to talk about LC circuits. So we've talked about inductors storing energy in a magnetic field. We've talked about capacitors storing energy in an electric field. So now let's talk about putting these two components together. So first, this was a very unrealistic model we're going to be looking at today because we're going to assume there's no resistance. And in reality, the really common circuit to look at is actually the RLC circuit, where there's also a resistance, but that becomes way more complicated to analyze, and that's usually done in a second course or an electrical engineering context. So if there's no resistance in the circuit, we'll actually see that LC circuits just continuously trade energy without loss in a cycle. So there's energy stored in the electric field between the capacitor plates, and that could be transferred to energy stored in the magnetic field and the inductor coils, and back and forth. And this will happen forever in a predictable time scale. So to first build our intuition as to why this should be the behavior of an LC circuit, let's give an example. So we're supposing that we're charging up a capacitor, making the top plate positively charged. We put it in a circuit, and at time t equals 0, we close a switch, allowing the capacitor to discharge through the inductor. So for each of these little snapshots of our circuit, we're going to draw the charges on each capacitor plate, the direction of current flow in the circuit, and then field lines representing the electric and magnetic fields near each circuit component, before drawing a sort of energy bar chart showing how our energy is distributed. So first, when the switch is first closed, we are given that the capacitor is fully charged and the top plate was positive. And as a result, we get a electric field between the plates of the capacitor. Which we're assuming is just points from one plate to the other. And then also, since this inductor will block any change in current, and there's no current originally, there is no current in the circuit right now. So for drawing our sort of energies, of course, we're doing it totally qualitative right now. So I'll just give myself 2 bars of energy stored in the electric field and 0 bars stored in the magnetic field at this time. Next, we'll look at a quarter cycle later when the capacitor's charge is first depleted. So this means that there is no charge on either capacitor plate. So as a result, there's no charge. But what that means is that there must be a current flowing through the circuit. And if we look at the direction, if we treat this capacitor like a battery, we would see that the positives would move around clockwise. So the current passing through the inductor must be oriented down through the inductor. And as such, there will be this magnetic field that forms around the inductor, also in the direction of current flow. So maybe we'll make it look a bit more like a bar magnet, just to show that. Just to show our magnetic field around the inductor coils here. So this would be the opposite, where a quarter cycle later, we have no energy stored in the electric field because the capacitor is not charged. But there is that same amount of energy stored in the magnetic field now. And there's nothing significant about choosing 2 bars of energy. I just have to show that it's the same as before. All right. Now, a quarter cycle after that, the capacitor becomes fully charged with opposite polarity. So now, after there's maximum current flowing through the inductor, Well, if the current is flowing this way, charging the capacitor, well, that's where positive charges would go. So when the current is at a maximum, these positive charges are actually going to the bottom plate of the capacitor now. But when it's fully charged, the current will be back down to zero again, because it's fully charged, so there can't be any more current adding to the charge. But the plates are charged to the opposite polarity, because the clockwise current would cause positive charges to collect on the bottom plate now. And now we still have an electric field between the plates because the capacitor is charged. It just also has opposite direction here. So this means, once again, we do have 2 bars of potential energy stored in the electric field and 0 bars stored in the magnetic field. Then a quarter cycle later, the capacitor is going to discharge, and this time the current will also reverse direction. So the current will continue to increase through this inductor as the charge is depleted from the capacitor. So once again, we do get a sort of bar magnet looking field here near the inductor. So we would get all of our energy stored in the inductor's magnetic field, and therefore 0 energy stored in the electric field of the capacitor plates. Because we have 0 charge on the capacitor once again. And then if we look back 1 quarter cycle later, we're back to the start. Because then this upwards current through the inductor is going to work to charge this plate with positive charges. So once again, we get our initial picture back. So the energy is all stored in the electric field again. So we see that there was this sort of trading of energies between the electric and magnetic fields here. And if the capacitor is fully charged, there's no current to further charge the capacitor. So we have no energy stored in the magnetic field, and have all of the 2 bars of energy are once again in the electric field. So of course it's not totally binary, like it's not all or nothing at all times in these circuits, but we just looked at convenient snapshots as to when all the energy was stored in the electric or magnetic fields. Because as the capacitor discharges, we'll still have a charge, but also some current. So that would be when your bars might not be all in one category. So now we'll try to graph this. So let's just go back and see what we had. So at t equals 0, the top plate of the capacitor had its full charge amount, and it's positive. Then the capacitor discharges, eventually leaving no charge and maximum current. Then the capacitor is charged up to the opposite polarity, and then it discharges once again, and the capacitor changes polarity once again, going back to its starting state. So what we should have is, again, physics always try to just graph points before we do any sort of shape or just end behavior. So we know that the top of the capacitor started with some charge Q max. A quarter cycle later, it was completely discharged. Then a quarter cycle later, it was charged to the opposite polarity. Then it was fully discharged a quarter cycle later. And then another quarter cycle later, it turned back to its original value. And now we can kind of have an idea as to what shape to connect this with, because we see there's something that's repeating in a cycle. And a decent guess for this would be that it's some sort of sine or cosine function. And now we'll graph the current through the circuit as a function of time. We could choose to use our graph for this or not, letting a counterclockwise current being denoted as positive. So first thing we saw is that at the start, since there was no motion of charges, there was no current flow. But a quarter cycle later, we had maximum current flow because all of the entire capacitor was discharged. But it was clockwise. Then, a quarter cycle later, the capacitor was fully charged, so there was no current. Then the current was maximized in the opposite direction, and then the current returned back to zero at the original state. And connecting this, we also get a sinusoid that's scaled by a different factor, but appears to also be shifted in phase. There's an alternate way of doing this graph that you may have noticed, where we're trying to find the relationship between the graph of Q of t and I of t. So notice that current is the rate of change of the charge through some cross-sectional area. So allegedly, the slope of my Q graph should give my I graph. And let's see. So we have zero slope at the start, then a negative slope, then it hits zero, then it becomes positive, and eventually reaches zero again. And that's exactly what we see. So just thinking conceptually, we were able to utilize this relationship that Q and I are related via a time derivative. So since I is dq dt, the graph of I of t is just the slope of Q of t. And then we can actually come up with like some rough expressions for Q of t and I of t, consistent with the graphs above. So we know they're going to take some sort of a sine form. So at first, the Q graph was maximized at the start and positive. So I'm just going to use a positive constant times a cosine curve. And I'm using cosine, so I don't have to deal with any sort of phase shift. And I don't know this angular frequency yet. I could also go a step further and relate this angular frequency to this time value here. So I could write omega is equal to 2 pi divided by t. I could also do that. We'll utilize this fact later, but we're just trying to get the general shape. We're not interested in the specifics right now. And then for I of t, well, let's look at I of t. So it starts at 0, so it's a sine curve, but also it initially goes down, so it would look like a negative constant I max times sine of omega t. And notice these are related exactly by a derivative. So actually, if we wanted to use this derivative relationship, you could see that I max is actually equal to Q max times omega by the chain rule. Because the derivative of cosine is negative sine, and then we'd have to multiply by the derivative of omega t, which is omega. And unsurprisingly, whenever we get a sinusoid, usually simple harmonic motion is involved. So from mechanics, a motion is defined as simple harmonic if we could write this differential equation, where the second derivative is proportional to the negative of the function itself. And it's just a fact that if this is your differential equation, your solution is some sort of cosine or sine. We won't actually mess with this phase angle in here because all of our sines or cosines will just be unshifted. So we could just use graph behavior to figure out whether we want sine or cosine. So most commonly, we'll just incorporate this fact that we could just shift a cosine by pi over 2 to get some sort of a sine curve. And this constant that shows up, omega, it's defined as 2 pi times the number of cycles that happen every second. So these are some equations to know. Several of them are on the mechanics section of your formula sheet. So omega is 2 pi f, and t is 2 pi over omega. So the time it takes for the circuit to complete a cycle is related to this angular frequency via this uh, pre-calculus relationship. And if we're getting sine and cosine as answers, that must mean that this differential equation must apply. And it does. It turns out that the differential equation looks the same for both charge and current. And it's given by the second derivative with respect to time is equal to this constant, negative 1 over LC, times Q, or times I. And just by doing some matching here, where we know that in the simple harmonic oscillator satisfies the equation that looks like the second derivative is equal to the negative of the angular frequency squared times the function itself. This tells us that this constant omega squared would be 1 over LC, so omega would just be the square root of 1 over LC. So this means that we can always write the charge on a capacitor or the current through the inductor as functions of time using some sort of sine or cosine curve. But this is usually not easy to deal with, like these time-dependent functions. So often what we'll do instead is the fact that we saw our energy bars had to be conserved. And we know what the energy is stored in a capacitor and an inductor. So we actually use this fact that the total energy at any point must be given by Q squared over 2C, which is the capacitor's energy, plus 1/2 Li squared, which is the inductor's energy. And those two things must be a constant when added together. Because we said when the capacitor stored a lot of energy, the inductor stored very little, and vice versa. So let's come up with these equations now. So first, it's the same one as before. We're just trying to come up with the differential equation. So first I say starting from Faraday's law, and actually I'm not totally a fan of starting just from Faraday's law, so we're gonna make a director's cut here. And we're just going to say loop rule. Because this application of Faraday's law will just turn into a loop rule. Derive a differential equation that could be used to give the charge on the top plate of the capacitor as a function of time. So for this, we will just apply the loop rule. So based on the loop rule, we know that delta V across the capacitor must be the same as delta V across the inductor because they're in parallel. So because they're in parallel, we can just write that their delta V's have to be the same. The delta V across a capacitor is Q over C, and the delta V across an inductor is negative L di dt. And that negative is accounting for Lenz's law. And this actually isn't where we'll stop because I can't totally see how Q and di dt are related. But we do know that that I is dq dt. So if you're taking a derivative of I, that means that di dt is actually just the second derivative of Q. So we could actually write Q over C is equal to negative L d squared Q over dt squared. Or if we wanted to rewrite this in the format that we were told to expect, we could get the representative equation that the second derivative of Q is equal to negative 1 over LC times Q itself. So the loop rule gave us one way of writing this differential equation. Now, we're going to come up with a differential equation for current as a function of time, and this one's also very easy. So if we take a derivative of both sides, again, we could also rewrite this as di dt is equal to negative 1 over LC times Q. So if we took a time derivative of each side of this, we'd get the exact same differential equation, because we'd get d squared I dt squared is equal to negative 1 over LC times dq dt, which is I. So this proves that we get the same differential equation both for the current in the circuit and the charge. But we'll get different answers for each that are shifted by constants and phases due to the fact that we'll have different initial conditions for current versus charge. But the more precise way of starting to get this differential equation would actually just be using the energy expression. So we said that E, the total energy stored, has to be equal to the capacitor's energy, Q squared over 2C, plus the inductor's energy, 1/2 Li squared. And these two energy terms have to be a constant together. So what this means is that the derivative with respect to time of this total energy must always be equal to 0, because the total energy can't be changing, although each of the individual energies certainly will. They just have to trade to equal this same constant. So 0 would be equal to the derivative of this whole thing. So if I take the derivative with respect to time of this, this can get kind of messy. We'd take the derivative with respect to time of q squared over 2c, and then we'd add the derivative with respect to time of 1/2 Li squared. But we know that this derivative better equal 0. So now we'll do some factoring out. So things like the capacitance and of course the inductance and the 2 won't depend on time. So I can write 1 over 2c times the derivative with respect to time of q squared plus L over 2 times the derivative with respect to time of the current squared. So the weird part of this derivation for a lot of people is remembering we actually have to do the chain rule here because we have functions of t, but we're not taking derivatives of anything with a t in it explicitly. So the derivative of q squared would be derivative of the outside function. So derivative of q squared is 2q times the derivative of the inside, dq dt, plus L over 2 times same thing, derivative of the outside function, I squared would be 2i, times the inside derivative, di dt. And actually some nice things happen here. The 2's cancel, and we can start grouping some common terms. So 0 would be equal to q over c, dq dt is just I, so 2 over c, q over c times I, plus L di dt times I. So now since both of these terms share a common factor of I, we can cancel that out, and we'd get the same differential equation as before, where we'd get di dt is equal to negative 1 over LC times Q, and then we can just substitute our final expression that di dt is the same thing as the second derivative of Q with respect to time. So conservation of energy also gives us this equation. And then starting from our differential equation, derive an expression for Q of t and I of t. So this is just a fact that we know that it's going to be a sinusoid. So once we write the equation, we are just going to skip to the answer. And the work we have to do is figure out what sort of function works. Is it sine? Is it cosine? Is it one of the negative versions? So that's what we do here. So Q of t, well, our capacitor should start with maximum charge. So it has some charge, Q0. And if it's starting at a maximum and not 0, it's a cosine curve. But we also said that omega is defined as 1 over square root LC. So we could write this as Q naught cosine t divided by square root LC. So that's our function for Q of t. And then for our current, I of t would just be dq dt. So we just need to apply the chain rule here. So the Q0 isn't going to have an effect with the derivative. So Q0 times derivative of cosine is negative sine. And then we have to multiply by the chain rule factor of 1 over square root LC. So we would get negative Q0 over square root LC times sine of t over square root LC. So we can actually see the maximum current is equal to the maximum charge times this angular frequency omega. So there's our functions. And now we'll verify that the total energy in this system is actually constant. I mean, we know it is because we came up with a differential equation that shows it's constant. But just for the sake of doing this example, because I think it's kind of nice, verify that the total energy is constant here. So we said that the energy in this system is equal to 1 half q squared over c plus 1 half Li squared, which can be written as 1 half times the quantity q squared over c plus L times I squared, just so we don't have to mess with that 1 half. So now we're just going to plug in our expressions for E for both the capacitor and inductor energy. So first, the capacitor has a charge given by Q0 cosine of t over square root LC. And then the inductor has an energy L times the current squared, which was negative Q0 over square root LC times sine of t over square root LC. And we square that. So the fact that we have something being constant and sines and cosines showing up probably gives you an idea of what very famous trig identity is going to show up somewhere in the next few lines. So let's make sure that happens. So we get 1 half outside, and then we'd get Q0 squared divided by C times cosine squared of t divided by square root LC plus L times Q0 squared divided by LC times sine squared of t divided by square root LC. Because again, I squared that square root on the bottom, and now we see that the L on the numerator cancels. So we can also factor out a Q naught squared over C, and we get Q naught squared over 2C on the outside times cosine squared t over square root LC plus sine squared t over square root LC. And since sine squared plus cosine squared is equal to 1, we see that we do in fact get a constant energy, which is just the total energy stored by the capacitor when charge is at a maximum. This could also be written as 1 half times L times the maximum current squared. but we just showed it's constant. I think this is definitely just a lot of algebra, but I think it's interesting to show explicitly, and we get to use that nice little trig identity. So now we'll derive an expression for the period of oscillations, so how long it takes for a cycle to complete. This is just a relationship that T, capital T, is equal to 2 pi divided by omega. This is just an equation sheet formula. So we get 2 pi divided by omega, which was 1 over square root LC. So the fraction gets flipped, and we get 2 pi square root LC. So this says to complete a cycle in this LC oscillation, it takes 2 pi times square root LC seconds. And then for frequency of oscillations, we define the frequency as the number of cycles per second. So if it takes t seconds per cycle, it is 1 over t cycles per second. So we just flip. We just flip our value of t here. You could also use the approach that omega is 2 pi f. So now we'll rank 3 LC oscillators based on the time it takes each to reach their maximum charge. So in doing so, we just need to rank their time, which we said that time was equal to 2 pi times square root LC. So we're just ranking the quantity of the product LC. So first circuit, we have an inductor and a capacitor. So it's just sort of our base case where our time would be proportional to square root just LC. Circuit B, we have 2 capacitors in series, and adding capacitors in series is a distance increase, so it actually decreases capacitance. So again, it's opposite the resistor combining rules. And then circuit C, we're adding capacitors in parallel, which is essentially making a bigger area. So capacitors, so the capacitance increases in parallel. So just by factoring out the constants, so we can just compare here. Circuit A is square root LC in its oscillation time times 2 pi. Circuit B would be 1 over root 2 times circuit A's time. And circuit C would be square root of 2 times circuit A's oscillation time. And again, I just dropped the 2 pi. Like if we wanted to actually compute the oscillation time for each, I'd give myself a 2 pi in front of all of these if we're just being complete here. But our lowest oscillation time would be circuit B with its 1 over root 2. Then we have circuit A, which had a leading factor of 1. And then we had circuit C, which had a leading factor of 2. So again, we had a 1 over root 2, and a root 2. So generally how we do these problems is not through the time functions, but rather just using energy. So we have a 100 millihenry inductor and a charged 2 farad capacitor are connected to form a circuit. At a certain moment of time, there's 10 to the minus 3 coulombs of charge on each plate of the capacitor, and 0 and 4 times 10 to the minus 3 amps of current through the inductor. So we have both types of energy here. So if we find the total energy once, we find it forever. So the electric field stores energy via Q squared over 2C, and based on our conditions in the problem, plugging in our 10 to the minus 3 coulombs of charge and 2 farads of capacitance, we get 2.5 times 10 to the minus 7 joules. And then the energy stored in the magnetic field of the inductor would be the 1/2 Li squared. And using the 0.1 henries of inductance and the 4 times 10 to the minus 3 amps of current, we get 8 times 10 to the minus 7 joules for the magnetic field stored energy. Calculate the ratio UE to UB at this time. So what ratio? What's the ratio between the electric potential energy and magnetic field's potential energy? So this is just something to compute. So if we divide these two numbers, we get essentially 2.5 divided by 8, which is 0.3125. And it's just a ratio, so it's just a number. So this tells us the electric field's stored energy is 31% of the magnetic field's stored energy. So now we'll draw a quantitatively accurate bar chart. So we'll scale this. Notice we've had 2.5 and 8 times 10 to the minus 7. So we'll say this is 10 to the minus 7 joules. So a scale that makes sense. I might just do 2s or 2.5s here, I think. So my energy stored in the electric field was 2.5. And my energy stored in the magnetic field was 8. So 8 is a little bit bigger than 7.5. So I'll just do something like that. And now we'll calculate each of the following quantities. So first, we want to find the maximum charge on the capacitor. Then we want to find the maximum current through the inductor, and then the period of oscillations. So first, we'll use the fact that total energy must be constant. So we'll use the fact that E, the total energy, is going to remain constant. And that's just going to be, well, these two things added together. So 8 and 2.5 make 10.5 times 10 to the minus 7 joules. So we'll use this fact that this is the total energy we're allowed to budget between our two bars. Well, the maximum charge will occur when all of our energy budget is spent in the capacitor's electric field. So we can set the energy just entirely equal to Q squared over 2C. And we'd multiply by 2C and then take a square root. So Q, we'll call this Q max. It's just the square root of 2EC. And that's equal to 0.002 coulombs. And then the maximum current through the inductor would be the exact same procedure, except the maximum current occurs when we're spending our entire energy budget on the inductor's magnetic field. So multiply by 2, divide by L, take a square root, we would get I max is equal to the square root of 2E divided by L. And that's equal to 0.0046 amps. So that shows how to, this is the most common LC circuit question I see. It's like finding the maximum charge or current. And we should just set the total energy, which we've computed at some point, equal purely to Q squared over 2C or 1/2 Li squared. And the period of oscillations T, well, the period of oscillations is just defined as 2 pi divided by omega, which would be the same thing as 2 pi divided by 1 over square root LC, which is the same as 2 pi times square root LC. And plugging in our values of L and C, which we already know, we get 2.81 seconds as our oscillation time. Okay. And now we'll look at a more complicated case of how we could get an initial current instead of just an initial charge. So we could also start with the inductor having current and not the capacitor having charge. So we have a common two-switch setup here where we're first going to flip the switch to position 1 and wait a long time so this inductor will reach steady state current. And then after that, we'll flip instantly to position 2 and LC oscillations will occur. So we know that the inductor will maintain this current as soon as it's flipped to position 2. So we just need to find this sort of steady state current through the inductor. So we know that after a long time, an inductor just behaves like a gap, or sorry, like a short circuit. So we know that we'll just use a basic Ohm's law to get that our steady state current, which will be the initial current through the circuit due to properties of inductors, is the EMF divided by R. And by initial current, we mean initial current as soon as the switch is flipped to position 2. So the initial current in state 2 should be the final current in state 1, which is the steady state. So now we can find the maximum charge on one plate of the capacitor using the fact that we just got info that at the start we have all the current we could possibly have through the inductor and nothing on the capacitor. So we can equate energies. So we could say that the 1/2 Li squared energy at the start plus the 0 Q squared over 2C energy is equal to the 0 energy stored in the inductor when the capacitor is fully charged plus the Q squared over 2C for the capacitor. So this is just our energy bar chart where we're showing that we can have a lot of bars in the inductor at the start and nothing in the capacitor, and then we can have all our bars in the capacitor. And we're solving for Q max, so we're just solving 1/2 Li squared is equal to Q squared over 2C. Notice the 2's cancel. So we would get Q is equal to square root of LC times I squared. And we found what this maximum current was. We said that the maximum current I was equal to the battery EMF divided by R at this steady state. So we'd get the EMF divided by R times square root LC. Because we'd be squaring I and it's in the square root, so we can just pull the current out. And then we'll look at the time required for the capacitor to first reach maximum charge after it's been flipped to position 2. So all of these major events occur a quarter cycle apart. So at t equals 0, we have current flowing down through the inductor. Then a quarter cycle later, the inductor releases all of its energy, so the capacitor plate is fully charged. Then a quarter cycle later, the capacitor discharges, sending its current the other way around the circuit. Then the capacitor's fully charged the other way, so it discharges in the original current direction, and we're back to where we started. So this is all happening in quarter cycle intervals. So all we're solving for is this time t required. It's just a quarter cycle. Everything in this sort of oscillation typically happens in these quarter cycle intervals, is when you get all or nothing for your energy. And we've derived this multiple times already. The time required, the oscillation time is 2 pi square root LC. So we just divide that by 4. So we can get pi over 2 square root LC. And then some conceptual things to end with. Consider the moment the capacitor first reaches maximum charge. So again, the current would originally be flowing down, so we're going to have positive charges be flowing that way. So we will have the bottom plate of the capacitor being positively charged at this moment. So draw the signs of the charges on the capacitor and the electric field between the plates. So we know the bottom plate is positive, so therefore the top plate is negative, and the electric field points from high potential to low potential, or the positives are sources and the negatives are sinks, however you want to see that. So justifying that, we see that the initial current is downwards through the inductor, so the current is counterclockwise, so this means the bottom plate, not place, of the capacitor is receiving positive charge, and as a result, the electric field points from positive to negative, so it's just upwards through the plates. And then, is the inductor storing energy at this time? Well, we just said the capacitor is at its max charge right now, so that means all of my energy budget is spent on the capacitor, so I have zero energy left over for the inductor. Or even more simply, when the capacitor is fully charged, there is zero current. And if there's no current, there's no energy stored in the magnetic field because you can't make a magnetic field without current. So we have zero energy stored for that reason. Because there's no current, which means no magnetic field, which means no energy. So here's our timeline. At t equals 0, we flip the switch for the first time, creating an L over R circuit, where the inductor will oppose changes in current, it reaches steady state, and at T1 we move to position 2, and then at T2 the capacitor is fully charged for the first time, and then the capacitor gets fully charged for a second time at T3. So we're going to graph this situation. So what I know for sure is that since it gives us that we're flipping the switch at a time much, much bigger than L over R, we're assuming this steady state current is reached. So I know that inductors are going to block current at the start because there is no current originally, so it blocks the current. But then at T1, I need to have this sort of maximum current that's reached. And the capacitor is totally irrelevant up to this point because it has not been connected in the circuit, so we just know this is going to behave like our typical inductor resistor circuit, where we have the maximum steady state current of the battery EMF divided by R. And we're assuming that this time is much, much bigger than the time constant of the circuit. So I'm going to make it really pronounced that steady state has been reached. So again, it's that exponential sort of climbing graph. So then we know that when the capacitor is fully charged, that means there's no current. So both at T2 and at T3, we have no current in our circuit. And then we're also defining our usual current conventions in terms of sign. So we know that the inductor will maintain the original current direction. So the current is going to decrease through the inductor as the capacitor becomes charged. Then when the capacitor discharges, it happens in the opposite direction before the capacitor becomes charged again, creating the current as 0. So we have like this exponential part when it's an L over R circuit, and then we have the sinusoidal part when it's an LC circuit. And then suppose we added another capacitor in parallel. Describe how our graph would change, if at all, in each of the regions. Well, first, if we use a bigger capacitor in the part of the circuit that doesn't involve the capacitor at all, meaning the less than T1 part, well, there's no change. So the effective circuit is really just an L over R circuit. Like the fact that at these short times or before we flip the switch, like it's just this circuit right here, that capacitor is completely irrelevant. So I don't care if there's another one added in parallel. But then what would happen to the graph at times bigger than T1? So first of all, we can see that adding capacitor in parallel, an identical one at least, would double the capacitance. So we know that what's happening here is that C is turning into 2C. And the relevant equation here to look at things involving shape would be the fact that this period of oscillation T is proportional to square root LC. So actually increasing the capacitance will cause the period of oscillations to increase. So adding a second capacitor will actually make this graph take longer to oscillate. So how would our graph change after that? Well, the cosine curve in this second portion would be spread out over a longer time interval. So this T2 and T3 would both be shifted, where the time between these events would significantly increase. Well, it would increase by a factor of root 2, I guess. And then there's other changes we could look at as well, but those are the primary ones. And lastly, what stores more energy? The original arrangement with just a capacitor, or the second arrangement with two parallel capacitors? And here's where it's really important to look at the initial conditions, because, well, part of us would see this fact and think, well, if we have two capacitors wired in parallel like this clearly stores more energy because it's the same potential difference, except there's double the capacitors. But the capacitors weren't charged originally. So our entire energy budget is dependent on this steady state current through the inductor as soon as the switch is flipped. So actually, the energy does not change because the initial current does not change when the LC circuit is created. The energy would only increase if we started by charging the capacitors to some voltage. So this actually stores the same maximum energy because the initial current has not changed. So if we wanted this to store more energy, you would have to start with the capacitors being charged instead of the inductor having current through it. And there it is. Inductor capacitor circuits, the final E&M section, complete.